Thank you for the opportunity to present. This was a collaborative effort between myself and my two co-authors. In particular, I would like to acknowledge the contribution of Paul May, who led the Jedi interpolation work in the Black Hills. Paul has since left the USGS for a postdoc at the University of Maryland supporting the Jedi mission. When mapping vegetation, we are all used to looking at two-dimensional depictions of the landscape. These are informed typically by passive optical data and divvy up the landscape into pixels. We've related the spectral data to various metrics that help us quantify vegetation, cover, LAI, biomass, what have you. But in essence, what all these metrics are telling us is basically how much stuff is there. In this case, the darker the pixel, the more stuff there is. Some of these metrics perform better than others, and they may get at slightly different things, but that's largely what it boils down to. And it works pretty well. Much mapping and decision-making has been informed by such products. However, what these two-dimensional maps fail to tell us is the vertical arrangement of that stuff within the pixel or across the landscape. Is it all tall vegetation or all short? Is it very heterogeneous or more clumpy or gappy in nature? And there are various applications for which this additional information is key. In the wildfire realm, it is critical for accurately estimating fuel loads and for modeling whether or not a fire will propagate from the surface into the canopy, or for assessing burn severity. Structure information can also help with assessments of forest regrowth after a fire. By now, I know we're all familiar with lidar and its rather unique simplicity in measuring forest structure. Here you see an example of lidar point cloud from an airborne system, and not a particularly dense one at that. These data are great for assessing canopy surface structure or what is happening at the top of the canopy, but can also help us inform what is happening to features within the canopy. If we had these data everywhere, we'd be able to derive a great wealth of information. However, that's not the case. This is a figure of lidar availability from the USGS 3DEP program as of this month. Much of the country has been covered, but there are still significant gaps, especially out west. Granted, other non-3DEP collections are also available, but when doing regional to national level mapping, having consistent collection parameters and data processing in place is immensely useful. So our group has started looking at the utility of space-based lidar to support the mapping and monitoring activities we wish to undertake. There are currently two systems on orbit, but for this talk, I will focus on Jedi. Jedi, or the Global Ecosystem Dynamics Investigation, was launched December 5th, 2018, and sits on board the International Space Station. The Jedi instrument includes 3 identical near-infrared lasers. 2 are used at full power, while the other one is split into 2 beams for a total of 4 beams. Each of the beams is optically dithered across track to create a total of 8 ground tracks with between track spacing of approximately 600 meters and a total across track width of 4.2 kilometers. The average along track distance between the footprints is 60 meters and the footprint size average is 25 meters, resulting in almost continuous along track coverage. The Jedi lasers emit light at 1064 nanometers, and they pulse 242 times per second, firing short pulses of light down towards the Earth's surface. Shown here is a sample Jedi waveform on the left. The light brown area under the curve represents return energy from the canopy, while the dark brown area signifies the return from the underlying topography. The black line is the cumulative return energy starting from the bottom of the ground return, normalized to 0, to the top of the canopy, normalized to 1. Relative height, or RH metrics, give the height at which a certain percentile of return energy is reached relative to the ground, defined as the center of the ground return. The diagram on the right shows the distribution of trees that produce the waveform on the left. Jedi science data products include footprint level and gridded data sets that describe the 3-dimensional features of the Earth. The ones we have been exploring include the level 1B geolocated waveforms, the 2A relative heights, and the 2B canopy cover and plant area index values. The Black Hills of South Dakota and Wyoming have been our primary study site. They encompass approximately 12,000 square kilometers and were sampled by over 500,000 Jedi footprints at the time of the analysis this past summer. Several landowners with different management objectives manage most of the land in the hills. The area is dominated by ponderosa pine, taller and denser to the north, shorter and more open to the south. The area is also impacted by both human-caused disturbances such as harvesting and natural disturbances such as wildfire. Additionally, mountain pine beetle infestations impact the area cyclically and also affect forest structure. As of this analysis, within the Black Hills, Jedi has covered about 2.5% of the land surface. So while this is a tremendously rich data set, there is still need for interpolation to generate spatially continuous products. For this, we are using predictive modeling. A predictive model is trained where the direct measurements, in this case Jedi, and ancillary data, such as Landsat imagery, overlap. And then the spatial continuity of the ancillary data is used to make predictions at locations without direct measurements. In this way, we can exploit Topler's first law of geography, which states that everything is usually related to all else, but those things which are near to each other are more related when compared to those that are further away. And we can see that typically in weather maps, such as the one shown here, where cooler temperatures are usually associated with other cooler temperatures, warmer temperatures with other warmer temperatures. All the predictive functions currently employed in the literature have substantial error when predicting at the 30 by 30 meter resolution of Landsat. This motivates exploiting patterns in the error to further refine predictions. The spatial correlation in the error is useful in that it can be used to interpolate. For example, if the predictive function is on average underestimating within a particular locale, all predictions within that locale can be refined by adding a positive adjustment proportionate to the degree of the underestimation of the nearby error terms and to the proximity of the prediction location to the nearby error terms. Traditionally, the use of kriging has been limited by its computational complexity. Cubic growth of the required operations and therefore computation time renders naive computation of the kriging weights infeasible for sample sizes of greater than approximately 100, which is of concern for many remote sensing applications. However, methods have been developed for fast estimation of the spatial correlation parameters and computation of the kriging weights. These methods usually entail approximating the original spatial correlation function in such a way that computation is fast, while the difference in the approximation and the original correlation function is negligible. Here we focus on the 95th percentile relative height from Jedi. Along with the Jedi data, Landsat 8 imagery from September 4th, 2020 was used to generate a canopy height map for the Black Hills. The data were first interpolated to build a spatially continuous product using a regression tree approach. To validate the predictive performance of the proposed method, 10% of the data were withheld from the training data as test data. This set of figures shows plots of the coordinate locations for the training and test data for the entire Black Hills on the top and a sample 10 by 10 kilometer area shown on the bottom. A regression tree was calibrated on the training data. Predictions were made at the test locations using the calibrated regression tree alone and also using the calibrated regression tree in addition to the interpolated errors using kriging. Here we see plots of the predicted canopy height at the test locations using the regression tree and kriging, as well as the true canopy height of the test set. To better understand how the regression and kriging are interplaying, here on the left, we see a heat map of the theoretical variance of predictions within a 1 by 1 kilometer sample area. On the right is a plot of the theoretical variance versus the distance between the prediction location and the nearest Jedi observations. As this distance increases, the variance reverts to the original variance of the regression tree. Shown here is the final predicted 95th percentile relative height map for the Black Hills. The accuracy values provide a reference for how well the interpolation methods predicted Jedi observations. It should be noted that the Jedi footprints are geolocated with some error, an expected standard deviation of 7 to 8 meters, which has a negative effect on model training, predictions, and mapping. There is still more validation work to do. Just recently, 3-depth airborne lidar data for the Southern Hills was released, enabling us to conduct comparisons for the whole region and also coincide with field data that were collected. Additionally, to improve results, the geography could be subset by vegetation type, and additional ancillary layers are being evaluated for inclusion, rather than just using the Landsat imagery. On a different tack, we have also taken a quick look at pre- and post-fire Jedi data to see if there are differences in vegetation structure characteristics. Here we show data from the Williams Flats fire, which burned in August of 2019 in Washington. On the left, you see the classified burn severity map with the location of the pre-fire Jedi footprints, and the map of the right overlays the post-fire Jedi tracks. Homing in on individual footprints, one pre-fire and one post-fire, in an area that experienced high burn severity, we see clear difference in the distribution and amount of vegetation material, in particular, a removal of surface vegetation near the ground. Looking at box plots comparing post-fire Jedi data by burn severity class, one can see a trend repeated in several Jedi metrics. As burn severity increases, the 95th and 50th percentile relative heights decrease, as does the waveform-derived cover value. Further work is needed on this and other fires to better understand how Jedi can capture relevant pre- and post-fire metrics and how those can be used to quantify values of interest. But indications here show that the data are sensitive to these disturbances. So again, these are just preliminary looks to start testing some of our own assumptions. We are continuing our work to see what more can be gleaned from the waveform data and how this might be used to advance the mapping of burn severity and fuel snapping. Thank you.